Hi there, this is Electric Fields. This is lesson 2. It's on Coulombs Law, part of the A-level physics. So let's have a look. What is Coulombs Law? The force between 2 point charges is directly proportional to the product of the charges, inversely proportional to the square of their distance apart, and is a maximum when the charges are separated by a vacuum. So you might realise that this is the same as the gravitational force, but just in terms of charge instead of mass. So for gravity, it will be directly proportional to the product of the masses, inversely proportional to the square of the distance between them. So Coulomb's law is the electric field equivalent of Newton's law of gravitation. So what is Coulomb's law? Well, mathematically, the force is directly proportional to the product of the charges, so Q1, Q2, and inversely proportional to the square of the distance between the charges. The constant, so if we get rid of this proportionality, the constant is a bit of a strange one. It's 1 divided by 4 pi epsilon naught, which is a constant, multiplied by charge 1, charge 2 divided by r squared. Now that version of the equation is fine. Epsilon naught is normally given on any respective data sheet, and it's 8.85 times 10 to the minus 12 farads per meter. If you're not sure what that is, once you've studied capacitance, you surely will. We can tidy that equation up. You can do another version where you just write Q1, Q2 divided by 4 pi epsilon naught r squared. Sometimes, however, in fact, I'll just let you write that down if you want it. So that's the equation. Force is measured in newtons. Charges are in coulombs. Distance is in meters, and epsilon naught is farads per meter. So the units are okay. Sometimes, however, I'm just going to get rid of this, show you another version. So we've got the original equation, the 1 over 4 pi epsilon naught, Q1, Q2 divided by r squared. So the 1 over 4 pi epsilon naught, if you put that in your calculator, so if we do 1 divided by 4 pi times the 8.85 times 10 to the minus 12, you get 8.99 times 10 to the power 9. So what you can do is just remember that, and then obviously that's the constant, the 1 over 4 pi epsilon naught, so you could just write it as force is equal to K, Q1, Q2 divided by r squared. Bit of an easier format. The drawback is that you have to remember what K is, and this is K, 8.99 times 10 to the 9. Whichever version that you use is completely up to you. I prefer the one where I use K. I just remember the constant. It makes it easier to deal with and easier to manipulate. Let's move on. Quick question then. Calculate the force between 2 small charged particles, 50 centimeters apart in a vacuum. One of the particles carries a charge of 5 microcoulombs and the other a charge of minus 7 microcoulombs. So you want to pause and have a go, and then I'll take you through it. So nice and straightforward. F equals, I'm just going to use K, Q1, Q2 over r squared. So we've got, it says 9 times 10 to the 9, but I'm going to use the 8.99 times 10 to the 9 times charge 1, which is 5 microcoulombs, 5 times 10 to the minus 6, times minus 7 microcoulombs. All this is going to do, the minus, is make the answer negative. So 7 times 10 to the minus 6 divided by the distance squared. So 0.5 meters squared. So that'll give us a force of minus 1.26 newtons. The negative is just telling you that the forces are attractive, which makes sense because we've got a positive charge and a negative charge. Let's move on. Quick question. If you want to pause and have a go. Calculate the electrocyte force of attraction between the proton and electron inside an atom of hydrogen. So we've got the charge of a proton, the charge of an electron, their distance apart, and the epsilon naught. Remember, you could just use K, which is 8.99 times 10 to the 9. So the force is equal to, could be 1 over 4 pi epsilon naught. I just use K, so K Q1, Q2 over R squared. Just put the numbers in, 8.99 times 10 to the 9, multiplied by charge 1, 1.6 to the minus 19, and then multiplied by 1 minus 1.6 times 10 to the minus 19. Remember, that'll just give us a negative answer that tells us that the force is attractive, divided by the distance squared. So we've got 5 times 10 to the minus 11 meters. Make sure it's squared. That gives a force of minus 9.21 times 10 to the minus 8 newtons. So the negative obviously just indicates that the force is attractive. Let's move on to the second part of this question. If you want to have a go, just pause. Now it's calculate the gravitational force of attraction between the proton and electron inside an atom of hydrogen, and then compare your answer with the previous question. So we need to think back to gravitation. So Newton's law of gravitation, which we should have covered, F equals G m1 m2 over r squared. Then we just need to put our numbers in. So G is 6.67. 2 times 10 to the minus 11. On most data sheets, it's just given us 6.67 times 10 to the minus 11. Multiplied by mass 1. So we've got the 1.67 times 10 to the minus 27. Times mass 2, 9.11. Times 10 to the minus 31 for the electron. And then divided by the distance squared. So 5 times 10 to the minus 11. Make sure that's squared. That gives us a force of 4.06, obviously it's attractive, got the negative, 4.06 times 10 to the power minus 47 newtons, which obviously is exceptionally small. And to compare them properly, if you divide the numbers, if you do the force due to the electric divided by the gravitational one, we end up with 9.21 times 10 to the negative 8, which is the answer from the previous question, divided by the answer which we just got, 4.06 times 10 to the minus 47. We end up with a ratio of 2.27 times 10 to the power 39. So that shows that the electric force is, to the order of 39 times more significant. Therefore, gravitational attraction is insignificant at the atomic level. This is very important. Okay, let's move on. Practice question. So if you want to pause and have a go at this one, and then I'll take you through it. The force on a charged object, 2 centimeters from the surface of a Van de Graaff dome of radius 10 centimeters is 36 millinewtons. What will the force be when the object is at a distance of 14 centimeters from the surface of the dome? So for this one, it may be beneficial to draw the dome. I'll just give a sketch. So 2 centimeters from the surface and the radius is 10 centimeters. So the distance from the center then is 12 centimeters. And then 14 centimeters from the surface. So 14 centimeters on the surface plus the 10 centimeter radius, which I just crossed out by accident, gives a distance of 24 centimeters from the center, so 24 centimeters. Now, what you need to realize is that is double the distance, and so the force, force is equal to, just do a proper explanation, K Q1 Q2 over R squared. So force is inversely proportional to distance squared. And what we've essentially done is double the distance. So if we double the distance, obviously we've got to square it. So 2 squared is 4. So that means that the force will go down by a factor of 4. So 36 millinewtons divided by 4 gives us a force of 9 millinewtons, 14 centimeters from the surface. Hopefully that went okay. One last question. Bit tricky, this one. So a charged, if you want to pause, please do. A charged metal-coated polystyrene ball of mass 6.3 grams suspended on a fine thread settles at an angle of 10 degrees to the vertical when a charged rod is brought close to it. So figure below. Part A then. What is the size of the component of the tension that opposes the electrostatic repulsion from the rod? So the rod will push in this direction. So we want a tension that acts, in the opposite direction. So this component, the horizontal component of the tension. So what we know the weight is 6.3 grams. So we need to do 6.3 times 10 to the minus 3. And then times it by 9.81 to get that vertical force. So let's do that first. So we've got 6.3 grams, 6.3 times 10 to the minus 3, multiplied by 9.81. And that gives us the weight in newtons, which is 0.061803 newtons. And then we've got this angle. So now that we've got the 0.061 as the weight, that is also the vertical component of the tension in the cable. They've got to be equal and opposite because the system is in equilibrium. So that red arrow that I've just drawn is the 0.061803, etc. newtons. So then we just need to use trigonometry to get the horizontal force, because that is A, that's what we're looking for. That is the component of the tension that opposes the electrostatic repulsion. So a bit of trigonometry. So we've got this one, we've got the adjacent, we've got the angle, and we need the opposite. So opposite and adjacent is tan, so it's tan of 10 is equal to opposite divided by adjacent. So opposite is what we're looking for, divided by the adjacent is the 0.061803 newtons. So if we do that, if we take that up, so we do the 0.061803 times tan 10. So tan 10 multiplied by 0.061803. That will give us the opposite, which is what we're looking for, which is 0.011 newtons. Then part B says, what is the size of the repulsive force between the rod and the ball? Well, part B is also 0.011 newtons. They must be equal and opposite, because as we said earlier, those two forces acting in opposite directions must be equal yet opposite. And then part C, assuming the field is uniform. So we've got the charge, we've got the force, electric field strength. So electric field strength from lesson 1 is force over charge. So we just need to do the 0.011 divided by the charge of 230 times 10 to the minus 9 for the nanocoulombs, which gives us, sorry this isn't very tidy, it looks a bit busy, but we get 47 times 10 to the 3. 47 times 10 to the 3 newtons per coulomb. Hopefully that's all okay and you followed that. So thanks for watching, hopefully that's helped, and I'll speak to you soon. See you on the next one.